invite me here, and it is really a great honor for me to deliver a lightning talk this afternoon. And prior to the talk, Peter sent us like 4 questions. And to be honest, when I first saw those 4 questions, I'm a bit shocked. Am I supposed to answer those 4 questions? So I feel like those 4 questions, they are too big for me to answer. It should be answered by you guys. And originally, I also thought that the purpose of me visiting the university was mainly to learn from you guys and to learn from your talks, to learn from the discussions, and probably also to briefly travel around. I didn't expect that I'm being posted into such a position to answer those 4 questions. And also, many of you have already provided many answers, sort of insights into those 4 questions. So in my talk, my purpose is just to try my best to provide some additional thoughts, in addition to those that you have been provided based on my limited experience and knowledge. And I probably will not answer like all those questions. So first I will directly jump into the 3rd question about the open research questions. So again, I think you guys have discussed like many important research questions, but I feel like one of the questions that has been less explored corresponds to the problem of fairness. So according to my experience, so when I talk to some of the health scientists, I feel like they really care about those fairness issues. So they believe like those AI, although they believe that those AI algorithms, they might be effective, they might be efficient, but they do not believe that those AI algorithms, they can make fair decision rules. So for instance, just to consider like a very simple example. So suppose we have like 2 patients. One of the patients is like a very young patient, and the other patient is like an old patient. And suppose we can only treat like one of the patient. Now suppose we know that if we apply the treatment to the younger patient, he's or she's more likely to survive. Then an AI algorithm will, for the purpose of maximizing the efficiency, it will recommend the treatment to the younger patient. But that's not like a morally fair decision. So how can we develop reinforcement learning algorithms? How can we develop policy learning algorithms to ensure a fairness? And the next point, I guess it has been also mentioned by Annie and also Hao-Da and Tianxi in yesterday's work, and Maximo also discussed a lot on this. So it's about privacy. So medical data, they can come from multiple sites, and how can we pull all the data together to enhance learning while preserving the individual privacy? So I feel that's a very important question. And also that's related to like federated learning, which Maximo just talked about earlier, and it is also related to like a new recent concept on decentralized AI. The 3rd question, I think this is like a long-standing problem in medical health, and Susan also talked about this in the morning during the keynote speech. So I basically refer to this problem as like a double inhomogeneity problem. Now, if you consider like those mobile health applications, so the data structure is quite similar to the panel data structure. So on one hand, you have like multiple patients. Now, on the other hand, for each of the patients, you have like a longitudinal type data. It is like a time series data. So that data structure is very similar to like a panel data structure. And among different patients, we do have like those patients' heterogeneity, and over time, we also have like such kind of non-stationarity. So for instance, typically in medical studies, the treatments, they are decay, they will decrease over time. So that's one sort of non-stationarity. And the real world, it is always like a non-stationary system. So there are many other sources of non-stationarities. Okay, so next, some other open questions. So in order to obtain like a high quality AI system, so data is like the key to build and to train those AI systems. So how can we collect the data? And in statistics, there are some like research topics that are related to the data collection process, which it's like experimental design, and this also been discussed by Professor Kang Jian and also some others earlier. And also the second bullet point, active learning, this has also been discussed by Hao. So how can we adaptively choose which of the labels that we should annotate given the limited budget and time of those experts? And the second point is on data integration. So how can we develop transfer learning and semi-supervised learning techniques to combine the data together to enhance learning? And also, how can we incorporate the power of large language models to improve the learning? And that might also be related to the last point on knowledge distillation, which is also briefly mentioned by Hao. Okay, so the second question, how should an individual statistician get to contribute? Again, you guys have discussed, has proposed several suggestions, and I just want to add some additional thoughts based on your discussions. So firstly, I think it will be important to continue to learn those state-of-the-art techniques, and combining those techniques with your expertise may yield new algorithms, may yield new methods. And take my experience as an example. So in the past 4 to 5 years, I have been learning reinforcement learning from Susan and also from those computer scientists. And I have to admit that I learned a lot from them. And now, when I view reinforcement learning, I will not only view it as like a powerful machine learning algorithm for the purpose of policy learning, but I will also view reinforcement learning as a tool to solve like many other problems, to solve many other questions. And here are some of the examples. So in the firstly, in the past 3 to 4 years, I have been working on like ride-sharing company. And 5 years ago, I take an internship in the ride-sharing company. And I became interested in the A/B testing problem in the company. So how can we assess the effect of a newly developed policy compared to an old policy? And when I asked the company how do they do A/B testing, they told me that they use like a standard two-sample t-test. But standard two-sample t-test has its limitations. So if you consider the ride-sharing application, it is like a very complicated dynamic system. So if you use a two-sample t-test, it will produce like biased estimates. So basically, the ride-sharing is like a dynamic, highly complicated dynamic system. So the past treatments, they will also impact future outcomes. So if you use a two-sample t-test, it ignores those carryover effects. And what we have found out is that the reinforcement learning framework, it is a very proper framework to capture, to model those carryover effects. So that's one of the examples. And another example is related to what we refer to as a dynamic mediation analysis. So what if you have like a mediator that evolves over time? And that's also mentioned by Susan in the talk in the morning. So how can we assess the dynamic mediation effect? So what if the mediator not only affects the current outcome, but it will also impact like future outcomes? And again, we found that like the reinforcement learning provides a very natural framework to model those effects over time, to model those dynamic systems over time. Okay. And lastly, causal inference. So there's a line of literature on causal reinforcement learning in the machine learning. And next, some ongoing works. So again, I feel first bullet point. So we recently found that reinforcement learning, and in particular offline reinforcement learning, it is also a very nice tool that can be applied to solve the transfer learning problem. So we can borrow some existing like offline reinforcement learning algorithms to enhance the performance of transfer learning. So that's what my current ongoing work. And we have designed some simulation studies and found the proposed method works well compared to baseline algorithms. And finally, also IL is a very nice tool for constructing experimental design to solve the classical experimental design problems. So that point has also been mentioned by Professor Kang Jian in yesterday's workshop. And next, sorry. Go back. And another point I feel, I think during yesterday's discussion, so we have reached like a consensus that currently the statistics literature the statistical community focuses too much on the math and focuses too much on the series. And now I have been graduated. 5 years ago, I graduated from my PhD university from NC State. So if I look back to what I have done 5 years ago, I feel that I spent too much time, I wasted too much time in writing the proofs, in writing the series. In writing papers like with over 100 pages, so like 30 pages for the main text and like another 90 pages for the supplementary article, which probably no one would read those supplementary articles. So I just feel that I spent too much time on writing the proofs. If I think about what I have done 5 years ago. Now, in the past 3 to 4 years, I have been reading like those papers from the machine learning literature, from the reinforcement learning literature, and I feel in machine learning there's also like a group of theoretical computer scientists. There's also a group of theoretical machine learning researchers that write theory papers. And I found that they are very clever in writing a series. They are very clever in writing the series. So they focus on writing the simple series. So series under the simplest settings to demonstrate the main idea. So that's probably one of the practice that we can do. So just to give you an example, for instance, they welcome like those reinforcement, what I refer to as reinforcement learning alone series or deep learning alone series. But they will not consider like their combination. They will not consider like combining those DL and IL theory. So if you can demonstrate the performance of the algorithm, of the RL algorithm under a very simple scenario, why would you consider to incorporating it with deep learning? So I think that's one of the example. And also they will focus on very simple settings. They will focus on very simple settings to prove the series. So for instance, in reinforcement learning, typically people will focus on tabular settings. So everything is discrete. You have like discrete states, you have discrete actions, you have discrete reward. Of course, this is a very restrictive setting, but it is mainly used to simplify the analysis. And secondly, they will usually impose like those independent data assumption. If we think about it as a statistician, so data, they are generated from a longitudinal study. So how come the data can be independent? And those computer scientists, they also know that this is a very strong assumption. But they are still willing to impose this assumption, not because they do not know how to extend those assumptions, but because they feel like it is unnecessary to use like those mixing type conditions. And finally, like they also typically use like a finite hypothesis class assumption, so which basically means that the parameters that the value of the parameters that it can only take like finitely many values. And again, they know like this kind of assumption, they can be generalized to more like general VC type conditions, but still they are willing to impose those assumptions to simplify the theoretical analysis. So I feel like based on my experience, so if I think about this practice, I feel that these computer scientists, they are very smart in writing like those simple series to save the time to demonstrate the main idea behind this series. And finally, I think this point has also been mentioned a lot during yesterday's discussion. Now, if you think about the machine learning community, I think one of the reasons that it can achieve such a large impact is that they stick to those benchmarking data sets. So as Annie mentioned, they have like many publicly available data sets, and Annie mentioned like the UCI machine learning repository, and Susan also mentioned the OpenAI Gym environment, which is typically used in reinforcement learning. And by the way, I also want to add that it is an open environment, so you can also add your new environment to those modules, to those modules. And in the past 3 to 4 years, I have been working on the application of ride sharing jointly with Hongtu. And now we do have like some benchmark environment so that we can evaluate different type of reinforcement learning algorithms. So specifically, we have like designed a very simple environment to simulate the ride sharing dynamics. So 2 or 3 years ago, I taught like a reinforcement learning course at LSE, and at that time, I asked one of the PhD students to wrap up the code for designing those ride-sharing environment, and of course, like we use the money from the department to pay the student as a TA, but later we managed to upload the code to GitHub, so it can be used publicly. And we also use real data sets to construct simulators, real data sets to construct more complicated simulators to simulate the entire dynamics. And also, we have students sent to the companies as interns to get the real data sets to evaluate the different performance of the algorithms. So that's all for my talk. Many thanks for listening.
Talk, and now question. Oh, okay. I mean, he's a local person. We should give him opportunity. I'll come back to you guys.
Yeah, thank you very much for a very interesting talk. I just wanted to make a point on your theory and how much we should simplify it and so on. Just, I'm very much immersed in machine learning community personally. I much more work on machine learning than on statistics. And I could say that quite surely that within the machine learning community, currently people are really tired of the theory, which often is done just for the purpose of having a theorem. So people are oversimplifying the things to the extent that the theorem doesn't give any insight on anything. And I don't know, 4 out of 5 theorems which you can find in machine learning conferences will be like that. So that's why I personally suggest to be very, very cautious, because of course, if you have a simple model which gives you a lot of insight, that's very nice. But unfortunately, the current practice is that people study the simple model which doesn't give any insight. So that's a big problem actually in the community.
Yeah, thank you for the comment. And I'm referring to those theories that mainly used to demonstrate their main ideas, but under those simple settings. So if they can demonstrate their ideas already under the simple settings.
Yeah, I think I want to echo the point on this. I personally, I respect people doing theory, okay? And at least in the last 5 or 6 years, my personal view is about why I'm concerned about the people working on the theory is, you think about deep learning as an example. And if you look at all the papers approved so far, published so far, my understanding, they basically try to approach these very difficult problems from harmonics, analysis, this kind of method, functional analysis, right? But do you think that are the right mathematical tools to solve the problem? I personally don't agree. The reason that's also comments by other speakers, because do you think that's all the functional space we considered, and we put all these bound? Practically, it's useless for us to construct better architectures to improve the performance of deep learning in practice. Any of this theory works that way. That's my personal understanding. The problems. I talked with Weijie on this. Could you classify, could you prove a theory, really basically say this, because of these mathematical results, help me design better architecture for that purpose? In what sense? Nobody. That's the basic, I'm not questioning this. That's the reality we are facing these days. Maybe Susan has a different opinion, but that's my general comments on this.
Okay, so do you have any response to? he just finished. Hongtu just made it finish his comment. Do you have any response to this comment? I mean, just go one by one. No? Okay, like Hao-Da. Go next. Oh, Hao-Da will answer the question. I will give them response. Okay, that's fine.
Actually, we also need some theory, some areas. So I was involved in the CataGo development. CataGo is an open source version of AlphaGo. They are heavily used on the deep reinforcement learning and the Monte Carlo tree search. Right now, we improve it as the Monte Carlo graph search. But there's a key formula, the POCT formula. The POCT formula is the balance, the exploration, and the interpretation. But right now, there's no good theory to get this. Many of our development is just try different form of these formulas and tweak the parameters to improve the learning rate. So if there's someone develop better methodology, better theory on this, that can significantly guide on the Monte Carlo tree search algorithms. But actually, I have one comment and also one question for the talk. So you mentioned this double heterogeneity. But actually, there's a triple one. The third one is the patient preference. I want to share the story for here, the patient preference, because some patients, even for the same efficacy safety, some patients more prefer efficacy and another patient more prefer safety. Because the patient preference is different, they get another layers of the personalized medicine. But actually, this kind of very interesting thing is many years ago, when I was present the kind of ITR framework to our physicians, kind of dynamic treatment regime personalized solution. Our physician asked the question, why you assume the physician didn't make an optimal treatment decision? Because all these reinforcement learning is assume other physicians didn't make an optimal treatment decision, but optimize well the target. Physician asked me, why you assume we didn't make the right decision? Maybe you are wrong. Our physician makes the optimal decision, but we optimize for the different things. So the question that come out is, how can we, from the real world data, we can better learn the patient, if we assume the physician make approximately optimal decision, we can approximately learn the utilities of the patient preference or the physician preference for different type of the patient. That come out with some of the research or the reverse the reinforcement learning. And that added additional layers of this patient preference heterogeneities. They call it kind of triple heterogeneity. My comment for here is, when we deeply interact with the physician, a lot of times physicians really ask very good questions that motivate our research. But my question for here is, at the first part you mentioned the fairness. So I'm just curious, the fairness for the reinforcement learning is a real question or is not a real question? My point for here is, because all the reinforcement learning, we try to optimize the total reward. So optimize the total reward is if and only if we optimize for each of the individual person. If our model space is flexible enough, so our model space is the flexibility is increased with the sample size, and eventually we are going to optimize for each of the individual. I didn't see any of the fairness problem for here for the individual person. So what do you think about this?
Attention, can the speaker respond? Then you respond. Can respond first. I know that this is a very hot topic, but can you respond?
Yeah.
Is there any fairness question in the reinforcement learning when the patient space is large?
Thank you for Peter for summarizing the question. So firstly, I just want to respond to the comment that Hao-Da made. So for the physician's question, I think not all the data they are collected from those observational studies, and we also have randomized data collected from randomized trials. So in those data sets, the treatments they are randomly assigned, and the physicians they are not they are not assigning the treatments in those data sets. So that's why individualized treatment decision they can help. And also even if the physicians they make the optimal decisions, so you can also develop statistical learning methods to possibly to improve their performance. And also you have also mentioned like the inverse reinforcement learning. So that's another very good point on incorporating physicians' recommendations into this problem. So that's my response to your first comment. Now for the second question, I think so at least based on my experience, when I talk to some of the health scientists, they do care about the fairness issues in reinforcement learning. So you suppose like if you give like different decisions to different individuals, then people might worry like if the decisions that you make, they are biased toward certain race, towards certain gender. And I think that's a concern, at least based on my knowledge, from my interactions with a health scientist. Does that?
Anyone? But if your response is very relevant, I think it's
yeah, I think it's just fundamentally not right if your decision involves, for example, an interaction with race, for example, and they have very little data, so you are basically artificially downweighting them, right? Their contribution. Let's say you have 1%. So it most doesn't matter what their loss is. You're not going to amplify their effect. So I don't think that particular issue can be mitigated, assuming the true model is correct. The true model has an interaction, basically, let's say, between race and all the effect, right? So it's
Oh, okay. So I'm continuing about the theory. I just want to say we don't make a very kind of absolute, nothing is absolutely wrong or right. So I think Chengchun made a good point, because I think that point is that when we develop theory, sort of people know the general idea, that theory works. We don't need to take care of every details, every combination. We say it works. What's intuition behind it? So that makes sense. So you don't want people read 100 pages, understand the idea behind it. But also, I think what Hongtu is a little bit too extreme. I think I appreciate the theory, because we... No, it's okay. You can talk afterwards. I just feel like I'm also developed theory. Let's say red metric complexity, VC dimension, the error rate, convergence. It's important. Although in the reality, I have to admit, we all the rate to say when the number of subjects goes to infinity, when my error bound will happen, or number of observation, number of time points, right? This is very theoretical. Reality, I have a limited sample points. I have a limited number of subjects, right? This theory sort of, for us to say, okay, if we increase certain things, we get a smaller error bound. Arrow. So in that sense, I think it's useful, even though reality we might not achieve it. So I appreciate that all the people did a hard theory. I think we should see both ways. We shouldn't say this is absolutely wrong or right. It's really we have to, a lot of things can coexist. Our mind shouldn't be extremist, say we don't do theory. We don't need a theory, we just do application. Or the other one say, we just do theory, we don't need application. I think we need a balance. Yeah.
Short response.
I think she misinterpreted my comments. My comments is I really like think if you have a method, if you develop some math to help understanding why this method works. Okay. The problems I'm talking about deep learning is because all the other theory they developed doesn't help us at all. Be honest with you. Everything they started with is wrong. Why do I care about the theory based on the traditional harmonics analysis? Because your starting point is wrong. That's my case. I'm highly respect the people. I also do semi-empirical inference, all these things, empirical process. I'm not saying this theory is important. If we understand the problem well and basically develop the method, help us to better design and also have a better understanding why all the method we develop works in certain sense. Even in a simple example, okay, you prove the theory, tell you why I need to tune this a little bit and make this better, okay? That kind of theory is important. I'm the only question, I publish another 100 papers, and also suggestion, doesn't solve any of these simple examples on deep learning. Why do we need this 100 papers, in what sense? That's my comments, okay? You don't need to misinterpret my comment.
We got it, okay. Susan.
Okay, so I just want to walk into that little mud pie.
Who wants to join the debate? Okay.
Yeah, Xiping has to join. I was thinking of some paper I saw by Ben Yu, And it was a very applied paper, okay? It was a very complex problem she was working on. It's really applied and quite complex. But then what she did was she had a small proof in a very simplified setting, which illustrated the main idea why the algorithm she was developing should be good. And then she used it in that real life problem. And I think in that setting, the use of simple theory, like you were talking about, the use of a simple theory, it makes a lot of sense when it's instance-based research. That is, you have this applied problem, and the whole paper is about the applied problem. And you're just supplying the theory to provide insight. Of course, I like what Annie was talking about, too. I mean, it's great to have these more theoretical where they deal with all the edge cases, and they illustrate that, indeed, there's something substantive in with a broader stroke. I'm all for that. But there's just two uses of theory here. And to keep them straight in my head, I think it's useful.
Yeah. Okay, so yesterday we talked about communications with people outside of a community. And we see examples today how difficult it is to communicate among ourselves. So I was misunderstood by others. So a lot of people believe I'm quite extreme because they don't think I like math. They don't think I'm good at math. But actually, I really appreciate the theory. That's why I work with Hong Tu and other students, because they have better math. So I think we talk about we don't like methods for methods, or we don't like theory for theory. I think when you develop theory, you should solve some problems so that we can understand the method better and potentially improve the method. Mm-hmm. And some of the good examples in simple case, when we do the one-dimensional smoothing, you can see the evolution from simple method to more complicated method, including Chengchun's local regression. I think you can see sometimes, not always, okay? I think Hong Tu is right. Many theories, they just did theory for theory, but unfortunately, in order to understand complicated method like deep learning, a lot of people have wasted their time to actually lay foundation. And someday, somebody may be able to really solve the problem. But I think just one shot solve the whole complicated problem is probably too ambitious. So I'm not too against the theory, but I agree a lot of theory is really waste of time, but sometimes it's necessary as part of the scientific process.
Yeah, I just want to add, because something occurred to me during the presentation, is that it reminded me of Herman Chernoff, that we collaborated for a long time, and then sometime we were working on very applied genetics problems, and he ran simulations. He wrote our program in his 90s, and then but often he would like to prove things himself. Now that he is obsessed with theoretical result, is a one way to generate intuition and understanding from different perspective. And I think in both, like, we often talk about how many ways you can prove the central limit theorem. Like, we often joke about there's an undergraduate level, there's a master level, there is a PhD level, like different. But that's just a very superficial way of thinking why we prove theorem, because sometimes it gets lost on the students. The reason why these multi-version of the proofs of the same results help is that it reflect different intuition of this very important result. And the same thing with toy examples. And toy examples are important. A good toy example help intuition, help our understand why the method works, how it works. If it doesn't even work in a toy example, if you cannot even come up with a simple example to demonstrate the use of the method, you may not have thought hard enough about that. So, but when we only focus on toy example, then that message also gets lost on the younger generation, because they feel, oh, it's enough to have a toy example. So I think by the end of the day, I think Heping made a comment like in a private chat about it's not something we need to change the discipline. The discipline had a very nice principled way of studying the world. It's only need to constantly reminding ourselves how we started the discipline, how the discipline was motivated by the real need to study uncertainty, to connect data, to use a combination of mathematical model and probability model to describe the random phenomenon of the world.
Great. This is a very nice discussion, debate, and yeah, it's good to make a good communication and to understand each other. And we do have 2 questions online. I think we should respect their participation and then maybe start for a second question that's related to Chengchun's talk. And then the first question is related to Susan's talk. So do you want to respond to the first question? Yeah, the second one. Susan, you respond to the second one.
That's a very good question. I think there's a lot of advanced statistical.
Can you read the question first?
Yeah, sure. The question is that the student didn't take a stat degree, and can we recommend a roadmap of advanced statistical concepts that are crucial for these AI projects? So I think there are many advanced topics that you might want to consider. So for instance, like those deep learning techniques, those reinforcement learning techniques, and nowadays like those large language models. And I also would suggest that the best way to learn those concepts is to really to do a project related to these techniques to enhance your understanding of these concepts and techniques.
So I think the best person to answer that first question is Chengchun Shi.
Oh, it's for attention. Oh, sorry. It's 11:29.
Oh, so yeah, the question was because there's a lot of heterogeneity on how hospitals collect and store data, like, and if you want to leverage multiple hospitals, how can we put together like statistical analysis and inference to clean and work with the data? First, I would say I'm not sure how they store the data necessarily change our practice, but definitely how they organize the data and how, for example, like the coding systems differ will put in a lot of challenge. I think we just really have to be aware of the heterogeneity across, like particularly, for example, earlier I think someone mentioned like how the drugs are given within each of the hospital. They are very different. They actually have different protocols within the hospital system. Like when a particular patient come in, they have a rule to say that's a first, like how they should start, be treated, etc. So when you do that, like doing, for example, reinforcement learning, it's actually really interesting that certain paths will never be observed in the system. They don't treat this way. So you cannot even infer the what if. So that is a scenario that you really need multiple hospitals to co-train the RL model. But I think that heterogeneity definitely give us sort of like in the statistical field, a lot of, I think that's something we can work together to think about both the robustness and also, you know, what's uncertainty that we need to put forth. And I really like Susan's point earlier about the uncertainty. I'm just wondering, in the RL world, like, did people really look into, I don't necessarily care what's optimal. If there's uncertainty, what about the second optimal? What if the second optimal is a lot easier or a lot, you know, like patient preference? Exactly.
Yeah, a principled way is to use a POM-DP, right? Something akin to a POM-DP. It's like you're predicting a latent state, like the latent state of stress, or the latent state of overburdenedness, or, you know, whatever. So that would be the principled way, and that is impossible to use. Those algorithms are not implementable in real time. They're just not possible. So I think you could do this in a batch. You could have a batch procedure where you might do this, but online, they just don't make sense. So everything is about a poor man's version of the POM-DP. So if we think of a POM-DP where the posterior distribution for the latent state is normal, let's just pretend, I'm just pretending, then the posterior distribution has two two parameters, the mean and the variance, right? If it's a normal posterior. So what's the poor man's approach? The poor man's approach is to do standard RL, adding another feature. One feature is the posterior mean, that i.e. the prediction, and the second feature is the posterior variance, i.e. the confidence. And so I personally think, and we know people use the normal distribution in variational approximations, they use it. I personally think that that's going to be the one that someone's going to get it straight and it's going to be really nice. But that's where we're going, is I want a posterior, I want the first two moments. And maybe you could demonstrate to me that I need the first three because maybe the predictions are highly skewed. I mean, it could happen, right? Particularly in these more complex, you're in a much more, you have a lot more data, so you might want the third moment. But in my world, the data's so sparse and so noisy. If I can get the first two moments, I'm probably good. Of the posterior, am I making sense? Do I make sense? Yeah.
Jen, I saw you had a question, but I cut it off. Do you want to take an opportunity to ask a question, or are you too sleepy to ask any questions? Okay, sure. Now I want to exercise the power of the chair. I want to close this session. I'd like to take an opportunity to thank all the speakers, all the people who participated in the discussion. So we will take a